All right. So today we're gonna continue our discussion of path integrals in quantum mechanics. I'll start by a review of what we discussed last time. We talked about so in quantum mechanics, we're talking about this is the Heisenberg picture, right? So operators like Q hat. This is a free particle propagating in space, or if you wish, this is 0+1 dimensional quantum field theory. These are Heisenberg operators, so they're time dependent, and I can talk about these kets. What we're after is a propagator. Propagator is the amplitude for the particle to go from ket QI at time ti to ket QF at time tf. That's just what propagator is, right? Some field configuration initial time, some field configuration at later time. Here by field configuration, I mean Q of I, right? In quantum field theory, it would be some field configuration. A field in space-time, phi1 going to field space-time, phi2. Field in space and time going to another field configuration space. All right, we talked about, we saw that how we could write this propagator, this amplitude as a path integral on the phase space. So this is the functional measure. I'm you see a million notation for this. I might write it sometimes this way. I might write it sometimes this way. They're all path integrals. What these stand for is limit of n going to infinity of dqr r1 to, so it's infinite number of integrals, right? That we're doing over a path. Here, the path is in the phase space. All right. Then we said that if you happen to have a Hamiltonian as a function of p and q, that is p squared over 2m. What matters is the p squared in this, and it doesn't matter. Sorry, p squared plus v of q. What matters is that if the Hamiltonian looks like p squared over q squared over something plus v of q, that means that the part, if you plug that p squared term and up here, you could perform the path integral over p explicitly, because these are just Gaussian integrals. By shift of variables, you perform the integral, and you end up with this normalization that is awfully divergent. We talked about this, right? But I believe in this lecture, because I don't want to write this over and over again, I write this as sigma. I'll define it when I say it, right? So now in these situations where that Hamiltonian is simple like this, you end up with a path integral over space, which is, cartoon wise, you could view it this way. Now, what is this? It's a path integral over all space, all path from this point to this point. So of course, the boundary conditions are saying that QI and QF have to be these points, so the functions have to end here, and then the action associated to a path is the weight. It's a phase, of course. It's not like a weight. It's not probability, but it's a weight that we associate with that path, and path integral is just an integral over that. Good. One little comment here. One little comment here for you guys. Just this is stuff that I wish I was told when I learned this stuff. So all along we'll be talking about canonical quantization, right? Space and time that breaks the covariance. These for non-relativistic theories, it won't matter, right? But there is such a thing as a covariant phase space. I encourage you guys to read about this. And there's such a thing called covariant space. We could talk about the phase space without breaking the, say, Lorentz invariance. We're talking quantum field theory, right? And just if you want to remember a slogan for yourself, what is the phase space? Give me a definition of a phase space which is not in terms of x and p. Do you have a definition of phase space?
Where the probability distributions of your physical system.
No. So here are paths that evolve, right, in space-time. Why do we identify x and p's? If you tell me the x and p at a particular moment in time, you have given me the phase space points, right? Why is that important? The reason is that it will uniquely fix for me the evolution, right? So to every x and p, there is a unique solution to classical equations of motions. Classical equations of motion are second order, so you need initial conditions. And it goes the other way around. Every solution of classical equations of motion corresponds to this. It's 1-to-1. So I just gave you the covariant definition of phase space. What is it? The space of solutions to their classical equations of motion. Just keep it in your mind for yourself. Is that good? No, good. Just keep that in your mind. We won't have time to talk about covariant phase space, but that's something to know. All right. Any questions? This is actually not phase space necessarily. It's called pre-symplectic phase space. You have to do all sorts of song and dance, but there's a full understood theory. This becomes important when you're talking about covariant theories, right? All right. How did we perform the momentum path integral? Hopefully you recall. So the way we did it was, well, Hamiltonian, we're taking it to be p squared over 2m plus v of q. We did a change of variable. It's just a shift. It's the standard trick that we do to perform Gaussian integrals, right? And once you do it, you end up, well, I did this, right? I did this. Okay, good. So this is that signal thing that I was talking about. You see the normalization that comes out once you do these integrals, the momentum integrals. All right, so what's the net result? It's a path integral over all histories in space with this divergent quantity outside. And so stationary phase approximation. This is when I ran out of time. So what is the story of stationary phase approximation? I'm just going to quickly describe it in this box. Imagine you have an integral of the following form. You have an integral. Oops. Whoa. What the hell is going on? All right. No. You have an integral over a function g of x. Integral over domain R. So it's a function of on a line of g of x e to the power of I k f of x. Good. What are we gonna do? We're gonna try to assume for a second that k is very, very large. So what am I doing? I have an integral over a line, right? I'm given a function g of x, and I want to integrate this, but I'm multiplying it by a phase that oscillates rapidly in space, right? It's just oscillating insanely fast. In the approximation that k is very large, we want to approximate this integral. This is called the stationary phase approximation. It's intimately tied to another approximation, the saddle point approximation. The saddle point approximation is when you have this integral over R. Instead of a phase, you only have something like this, minus what they call it, k f of x. Is that how I called it? Yeah, d of x. Right? The saddle point approximation says that when k is an approximation for this integral when k is large, and the stationary wave approximation, stationary phase approximation is for when k is large for this integral. One of them is like Bessel transform, the other one is like Fourier transform, right? They're related. Okay, so what is it? Well, this might be more familiar. When it's like this, you basically find the critical points of the extrema of the exponent, and you evaluate the integral at the extrema. That is the dominant piece, and then there are 1 over k corrections. Why does that matter? What is k in physics? Often k is 1 over h bar. Right? H bar is small, so you're doing an h bar expansion. Here is similar, right? You have is action over h bar. In a path, as you go along the path, the h bar is small, so the phase is oscillating really, really rapidly. Sorry, I think I gave the wrong intuition. When the phases oscillate rapidly, it means that the value of the action on this and the value of the action very, very close by, as you deform this, they oscillate really, really rapid. Right? So that already tells you what is the idea. The idea is that when they oscillate very rapidly, the integral is dominated by the saddle point. Where it's by the saddle point when it's extrema, when the derivative is at 0. Right? So let me write down the expression. I have it here. So this says, this is a mathematical statement. This integral is well approximate. It is equal to sum over all the critical points of S. These are points where the gradients vanish. Either they are minima or maxima, it doesn't matter. They're extremal. Sum over all such points, the function evaluate that point, the phase evaluate that point. Now, there is this subtlety regarding the sign of the second derivative. And then there is the 1 over square root k correction to it that I've already put in. And then there are higher order terms. So look this up. I think it will be very important for your general physics education to understand stationary phase approximation and I think it's called saddle point. I don't know what to call it. It's a saddle point approximation in physics. Some people call it mean field approximation. All right. So similarly, here we have a path integral. H is very small, so this is rapidly oscillating. So the path integral is dominated by the case when S of Q is a saddle, right? Is extremized. What is it? What is the variable that we're varying? We're not varying with respect to a single variable here because this is a single integral. This is a path integral. So the extremization occurs when you vary S with respect to Q, a function worth of variations, right? When that is 0, then indeed your path integral is well approximated by that. This is the least action principle that we discovered or we discussed in classical physics. So path integrals give you an organized way of how to think of quantum mechanics as H bar expansion of the minimum action principle. Good. The critical points, yeah. This is extremely useful in physics. It's all over the place. Almost no matter what, unless you're an astrophysicist. I don't know what in astrophysics, I would think that you would also use it, but it's impossible to do grad school in physics and never use this. It's all over the place. Or if you didn't use it, you didn't understand the problem you were solving. All right. Good. Any questions?
So, in this expression, x naught there means like the second point.
Yeah. So x naught is a critical point.
Critical point means it has 0 derivative.
Yes. If it's a function, it's 0 derivative. If it's a functional, it's a 0 function variation. Right? Good. So this is a path, right? Least action principle inside the path, and it will give you a path for classical evolution. Good. All right. All right, matrix elements of observables. So here I'm going to do something that I was hoping to do. These are all the slides from last week. Okay, so let's just make a comparison between what you know of quantum, what you know, the standard operator approach to quantum mechanics that you're familiar with, Hilbert spaces and operators, observables, and path integrals. So I told you how the path integral, well, we derived the path integral as a way, as an expression for the overlap, the propagator. So now the question is, well, there's more, at least naively, there's more to physics than just the propagator. We would like to know the expectation value of observables. We would like to know matrix elements of observables. If I describe to you a path integral expression for the matrix elements of an arbitrary observable using the path integral path integral expression for it, it's a reformulation of quantum mechanics. Is that good? Okay, so here it is. What we're going to do, previously, we wrote the path integral expression for the overlap without the Q hat. Now let's just stick in an operator there. When you stick in an operator there, well, it's just pretty straightforward. This is in T prime, so T prime is between Ti and Tf, of course. So let's just immediately put a resolution of identity in Q prime. This is a standard propagator. This will just bring Q hat, Q of T prime will come out because it's an eigenvalue. So you'll get an integral over two propagators with a kernel. Right? So here's what you're trying to calculate. You first do you split it into two parts. The up to here, it's up to here because the path integral from here to here, I can perform this path integral as a path integral from here to this time T prime, and then from time T prime to Tf. Those are two propagators, and I integrate over Q prime here, right? So this is the expression for it. Does everyone follow this step? So I gave you the matrix element of a single operator. Here is some magical thing. This is for you to work out as a homework problem. What if, so that's just one operator that you put in time T prime. Of course, if you insert all your operators at time T prime, it will work out similarly. But what if inside the path integral, you put Q of T prime and Q of double T prime? When you do these inside the path integral, the order doesn't matter. Just these are integrals. These are not operators, right? When you're doing path integral, these are just integrals. These are just functions. The order doesn't matter. So what is this capturing? Well, this is a problem for you guys to figure out. Do it as a homework problem. You will see that this path integral represents the time automatically represents the time order operator. The expectation, the matrix element is the time order operator. Hence the name Feynman propagator. Remember, what was a Feynman propagator? Feynman propagator was time ordered. So the reason is that Feynman path integrals, if you just insert functions in there, what pops out is always time. This is an exercise for you to do. It's just pretty straightforward. But you just consider two cases. One is T prime is larger than double prime, and the other case, and you see that it switches the order. Good. This is a magical path integral. There are a couple of these are the reasons the path integrals are easy in a sense. There are a couple of things about path integrals that help. Any questions? Uh-oh. Good. All right. So this is what I started last time, but we ran out of time. We're gonna have time to talk about it. So, what is there? Is there such a thing as a quantum equations of motion? What are the equations of motion classically? Classically, equations of motion, well, are coming from this: del S del Q is equal to 0. Right? These are the classical equations of motion. Well, you could ask, well, S is a function, is that now S you could insert it inside your path integral and treat it as an operator. You could ask, is this an operator equation? Could this be an operator equation? Right? You just stick it inside the path. Is that clear? Do you know the answer in advance? It might be on the slide. It's a profound result that we're going to use to derive the whole perturbation theory. Actually, as a matter of fact, very formally, you could solve path integrals using the following fact I'm going to tell you. When you do an integral, x is a dummy variable, right? Any change of variable, x to x prime or whatever, if you're consistent with your boundary condition, change your boundary condition, it won't matter. It's independent of that. So, for example, if this is an integral over, what does that mean? It means that, remember the fundamental theorem of calculus? If you have something like this, right? Xi, xf, this is just xf minus f of xf minus f of x, right? Now inside inside the path integral, you could play a similar trick. Let me write it. Oh, sorry, I already go into quantum field theory. Sorry. I don't want to write it actually. Yeah, I want to write it x of t, q of t, q of t. Good. So if I have a whole bunch of things here, doesn't matter what. If I put delta del q of t, and then this is qi, qf, what is the value of this? Is this expression evaluated at q of f minus this expression evaluated at q of I. It's just that. It's the fact that x is a w vector. This has a name, Schrodinger Dyson equation. But for now, it's just sort of a triviality. Now, what are these delta qt's? These are variations in my path, right? So here is qi, qftf. If I vary with respect to path that don't change the endpoints as I want to do inside the path integral, what is the value of this derivative? Zero. Think about that. All right, so let's just put nothing here first. So we learned that this is going to be zero. But what is this? Just do the derivatives. You're going to get integral of s q of t del s del q t half integral d of q of t qi q of f is zero. Right? What is the interpretation of this? We just said that the interpretation of this is the matrix elements of this operator. Well, it's this. Good. So del S del QT as an operator has the following property. Every single matrix element of it in this basis are zero. Is zero. Everybody's with me? Okay. Here comes the important fact. This is something you might not know. It's a property of infinite dimensional Hilbert spaces. An operator could have zero matrix elements for a dense set of vectors, but the operator might be non-zero. You don't need to know any of that. I'm just gonna give you calculate for you other matrix elements in the stack. Okay, so hopefully it's clear that the matrix, every single matrix element of this is zero in the Q basis. Good. But what we're gonna do is this: we're gonna stick in some other operator over here. By the same principle, this is zero, but now you have two terms. You have del S del Q O plus, what is the other term? Del O del Q. The action is out. So the first term acts on this, right? The second term acts on that. Okay, so what did you learn? You learned that the matrix elements of here, let me just summarize the expressions here. I don't know why I just switched the board, but it feels right. This is zero. However, This is not zero. What is the second line? This is equal to minus Q of F, T of F, del O, del Q of T. So every matrix element of this object is zero. When you multiply this operator, well, by operators that are independent of the Q, again, every single matrix element is zero. But if you multiply by an operator that depends on Q, the answer will depend on the derivative. Well, okay, I just did this here. Somehow I put an H bar. I don't know where that took the H bar from, but I probably had normalization in my S's that had H bar. All right. Let's start this. What you see on the over there is just what I did on the board. This is called the Schrödinger-Dyson equation. This expression. If I write this, the first one is implied. Always like that. All right. Any question? Schrödinger-Dyson, you're gonna see we're gonna use it to solve, formally solve, write down all the equations of quantum field theory. It's very formal. But it's just like a simple statement. It's about the fact that X or field Q of T is a dummy variable inside the path. Questions? It's all good. All right. In summary, we're at the end of the last lecture now. The path integral approach to quantum mechanics is an alternative, an equivalent description of quantum mechanics. At times, it's easier. As a matter of fact, it's a lot easier to work with path integrals when you're doing for quantum mechanics, when you're doing perturbation theory. One of their main reasons is that correlators come out time ordered just naturally. So we, in our discussion, we went over the fact that we write down the propagator as a path integral. The path integral comes out as a phase space path integral. If your Hamiltonian is simple like this, there's the kinetic term is separate. You could just, and it's p squared, you could do the integral. That's all good. Oh, another thing I didn't say, but hopefully it's clear. The propagator is propagator is a green function for the Schrödinger operator. Right? This is the Schrödinger operator. Yeah. So here's the Schrödinger operator. Let's start this. The propagator is a Green's function for the Schrödinger operator. Green's function means that what pops out is Dirac deltas on the other side. Right? That's what it means. In general, hopefully you recall theory of differential equations. If you have, let's say this is L of X. Something like this is called Green's function. It's a differential operating X, and this is a function of two variables, and it's as a Dirac delta. Right? What's the point of Green's functions? Exactly. By integrating this against f of y, it's a solution generating method. If you integrate this against some f of y, that's going to solve your equations with your favorite initial conditions, right? Inhomogeneous. All right, we also talked about quantum observables, the operating insertions in the path integral, and then we said that we talked about quantum equations of motion. And all right, any questions? This is what we're supposed to cover last time. What are we gonna do in the remainder of this lecture? First, now we're gonna get our hands dirty and do calculations. I'm gonna do. I think I'll actually have enough time to do it. We're gonna calculate explicitly the propagator of a free particle in quantum. Free particle propagating in space. We're gonna call that K naught. Sorry, K naught. That's step one. Step two, we're gonna include interactions with some small coefficients. We're gonna come up with a perturbative small coupling expansion. What is crucial is that you will see, like what is a lot of people, it can lead to a lot of mistakes if you're not careful with what parameters considered to be small. So we're gonna write down expansion. We're gonna calculate the first order correction to it called K1. And I'm gonna give you a diagrammatic approach. This is, by the way, this is the baby 0 plus 1 dimensional version of Feynman. It's easier in 0 plus 1 dimensions. Maybe. But we're going to do it in 0 plus 1. It's quantum mechanics. You don't need to get into complications or anything else. But you see the same structure. Okay? We're going to do calculate the first order approximation, K0. What I want to stress a lot that often is not properly stressed is the fact that you should pay attention to what is the small parameter expansion. That's very crucial. Do you have a guess? What is your path integral? Is a path integral is an integral over all path? There's a measure. There's a phase associated to each path, right? That phase is what? That phase is e to the power of is q of t, right? Well, this is your action. There is the free action, and if you have interactions, there will be contributions to the action coming from interaction terms, right? We're going to see that the expansion is assuming that the interaction to action is smaller than the free action. Action. This is integrated along the whole line. All right, so the Gaussian free propagator. Imagine, well, this is the setup that we had. Our action is going to be just q dot squared, half m squared q dot squared. This is the Gaussian integral. So let's just split ti and tf into n pieces, delta t. And because we're discretizing, we can think of the values of q1, q2, all the way to qn minus 1. Those are the integrals in the middle, right? And it's a vector. Let's just as one-dimensional quantum mechanics, which is in the language of field theory. What is it? What's the field? It's a real scalar field in 0 plus 1 dimension. All right, very good. Here's the expression that we got by performing the p part of the path integral. Right, I've already done that part. This is that awfully divergent thing that I think I'll just refer to this as sigma over and over again. Now you have an integral over dqj, j from 1 to n minus 1 corresponding to these integrals. There's of course this sigma that pops up here once you do the path integral over momenta, right? Because once you complete the squares and use the integrals, there's sigma popping up here. That's very important, actually. Oops. Then you have qj minus 1 minus qj squared. What is this term? Just discretization of q dot squared. Good? Okay. Everybody's with me? It's all good? How do we do this? Well, look at this expression. I just already gave you the I said Q, think of it as a vector, an n-1 vector. All right, so then I can expand this and think of it as Q transpose dot M dot Q, this is M, plus A transpose A minus, well, okay, this is actually the most general thing you could write down. But do you see that this Q transpose M dot Q comes from this? Do you see it? Do you see it, or should I do it? Okay, good. You see it. When you expand this, there are the cross terms, and then there are the diagonal terms. Okay, very good. And this A is, we're adding it to just keep track of QI, QF. So this is what the A vector is. It's just rewriting of this expression. Yeah, it's just a line of algebra. How do you do the integral? You complete the square by shifting the vector Q prime this way. Now, after some algebra, which you're going to do in the homework, or if you're lucky, I might forget to include it, this is what it becomes. So in summary, K naught becomes the following expression: e to the power of minus pi sigma QF minus QI squared over n. This is coming from this term that popped out from the Q squared, the boundary condition, this A term. Sigma to the power of n minus 2, that is just this. And then the integral of dq e to minus pi sigma qi mij qj. Right, that's just, this is just like, this is just q transpose dot m dot q. Good. Now you just have a bunch of Gaussian integrals, and you just do it. The result is going to look like this. There will be, this is an interval you can do and you should do. It's going to be the, of course, there's a divergent piece that I'm neglecting for now. There will be a heavy side step function. I think that's what's called TF minus TI. Hopefully that's clear why. There will be m over 2 pi I TF minus TI to the power of half. This power of half has to do with the dimensionality of space. Here's 1, that's why it's 1. For those of you guys who take QFT2, these expressions will come back all the time. Actually, later in this course as well. And then this is the extra bit, right? So the result of this part of the integration basically gives us this part. There are things to pay attention to it. First, because of this step function, this is a retarded propagator. That shouldn't be surprising. Right? The other thing I want you to pay attention is that the propagator is dependence on QF and QI is QF minus QI squared with a phase. This is the green function for the free Schrodinger operator. Is it clear what I mean by Schrodinger operator? I think I showed it to you. Good. All right, any questions? These expressions will become, as physicists, will become part of your bread and butter. You'll be working with propagators and just knowing in advance all of these expressions. Perturbation theory is free. It's super useful to have the structure of these terms just fresh on your mind. Okay. All right. Okay, so this expression is the propagator for free particle in d-dimensional space, right? Just replace that half by d over 2, which is quantum field theory in 0 plus 1 dimension when your field is a vector with d variables, with it's a vector with d components, right? And this is a property. As it's written, it might look a little bit ugly. It's easier to write this down in Fourier space. Okay? But it's a function of, what is it a function of? It has QF, TF, QI, TI. Right? Staring at this, you already see translation invariance in both P and Q. Okay? All right. So it's really a function of two variables, QF minus QI, TF minus TI. I can Fourier transform this. That would be spatial momenta. I could Fourier transform this. It would be frequency. We'll do both. I'll do one by one. This is a non-relativistic particle, so you might find it confusing that we're Fourier transforming in omega as well. In covariant theory, quantum field theory, you want to do it in one shot, right? Like it's natural to write everything in terms of 4 momentum vectors, right? But I'll do it actually to make a comparison. To compare this with the previous expression for a propagator, you have to see, we have calculated the propagator for free fields, right? Remember that we did that calculation. What was the retarded propagator? What did it look like? We wrote it as an integral, which was Fourier transform. The retarded propagator in momentum, 4 momentum space, right, was an integral over K naught, complex K naught plane. There were 2 poles. We did this integral. Is this the one that we did or below? Below. I think it's this. That was good then. This is below or above? I don't know. That's fine.
Oh, okay.
That's fine. One of them is retarded, the other one is advanced. Okay? We use the fact that there was covariance to get rid of Q's, right? We always could sit in a frame where they were only time separated, and then we just had one function to work with. Here we're in non-relativistic quantum mechanics, so we're just going to treat them separately. Good? So let's do this. Okay, all I'm going to do is just Fourier transform. Here's the expression I'm working with. So the full transform of P of F is Q of F, and Q of F is P of F, and Qi is P of I. Here, I'm pretending I don't know, I haven't realized the translation invariance thing, but it comes out. It doesn't matter. So I just Fourier transform it in d of d. Hopefully you can see it. The way you do this is you define. Let me see. This is just like simple manipulations of Gaussians. You introduce 2 variables. One is the center of mass. These are the center of mass coordinates. You add and subtract p's, and you add and subtract q's. These are the things that you need to Fourier transform, right? Pf dot qf, pi dot qi. There's a minus sign difference. Is that clear why? As the propagator is qi ti qf. This one is the dagger. You could write this expression in terms of these center mass coordinates. All I'm doing is just, I could have treated this by saying that, hey, there's this translation invariance, so let's set some of them to 0 and do Fourier transform one variable, but I'm copying it from somewhere where they did this more generally. All right, here what it becomes. Of course, it will only depend on little x, but it's helpful to keep track of capital X. The capital X, you end up with a Fourier transform of this, which is just a Dirac delta function of P. What's the meaning of this Dirac delta function of P? In physics, every time you see Dirac delta function of P, it means conservation of momentum, right? Conservation of momentum. So momentum is a charge, conserved charge, associated to what symmetry? Translation symmetry. There you go. So the very fact that I have translation symmetry in time as well, that's just conservation of energy. You should expect a Dirac delta function of EF minus EI pop up somewhere. It's free particle after all. Well, it's not like if there were interactions, it would not hold, it would always hold. Energy is always conserved. Say it again. Say it again.
It would also correspond to the on-chip condition, right? If we had some Feynman propagators for particle creation and stuff like that for Feynman diagrams.
So here we're talking about non-relativistic system. There is a way of viewing it that way. Sure, there is a way. That's more like saying, yeah, okay. That's more like saying that, you know, like when you talk about the on-shell condition, what it does for you is that it gives you a dispersion relation. It relates energy to momenta. That means that if your momenta were conserved, your energies would have been conserved. Here we're just treating them as two different Dirac deltas, right? You could say those words as well. All right, so after the Fourier transform, I only did Fourier transform in spatial directions. What comes out is the Dirac delta of P, right? What is P? Remember, P is the difference between them, right? The difference, PF minus PI. That's why it's conservation of momentum, right? Step function of TF minus TI, and then e to the power of I, TF minus TI, P squared over 8 pi F. This is conjugate to time. So you can see in the next step, if I Fourier transform in time, this is the energy conjugate to time. So I can read off the dispersion immediately. It's non-relativistic as expected. It's just P squared over 2M. Maybe the 2M-ness of it is not quite clear yet, but good. But this is the expression for it. Propagator in spatial momenta and as a function of time. But of course, you could Fourier transform in time as well. And you're going to end up with EF and EI. These are the Fourier modes corresponding to TF, the canonical conjugate to frequencies, right? There's an H bar difference in between. You do this Fourier transform. I won't bore you. You can do this integral, these integrals. Hopefully you can. You define this variable, time difference in anticipation for time translation symmetry, and then T of I, and then of course you can do the integral over this variable. Now here's something funny, something important. This Dirac delta we already had, right? This was just conservation of momentum. This is stuff, old stuff. So let me not highlight. There is this bit and this bit. What does this give you? That integral over Ti, you can do explicit. What does it give you? Dirac delta. That's conservation of energy. So you found your conservation of energy. What remains to be done is an integral over d of tau with this phase. All right, that integral is a little bit ill-behaved. Do you see why? Yeah, at large t, large tau, it oscillates like crazy. So it's helpful to make this converge. It's helpful. This is something, by the way, that's standard thing in functional analysis, but as physicists, we usually say this, like, give the physics picture. We say To make this converge, we add a damping term, e to minus epsilon tau over h bar here. That will make this integral converge. We're suppressing the UV modes. We do that all the time. Okay? So, by the way, this is only legit if the final answer will be independent of epsilon, right? Epsilon is a cutoff in a sense. We would like independence of epsilon. Keep track of that. Okay? All right. So if you put an epsilon, this factor here, you could do the integral. It comes out in the following way. These are what we had before. This is the energy conservation. It becomes IH bar over EF minus PF squared over 2M plus I epsilon. Now, does this look familiar? This is similar to the I epsilon of the Feynman propagator we discovered. In the Feynman propagator, what was the I epsilon prescription? It was 1 over k squared, what was it? K mu. Well, actually, let me write it this way. K squared minus k0 squared. Let's just write it. K0 squared plus I epsilon. This is now replaced by the non-relativistic version. In the relativistic version, we said that we have two poles. There are two, we said that, well, there are two poles, right? There was the minus omega k, omega k. We just wanted to integrate these two guys. And then we said we're going to deform the contour and integrate below. Right, this is what we did. I already explained to you that this deforming the contour is like that e to minus epsilon. Okay. So the fact that it has to be independent of epsilon means what? Means that I can integrate this down here, the result won't change. I can integrate up here, the result won't change. What does that mean about the 2-point function? When are you allowed to move the integration like this? Analyticity. There are no poles here. Analyticity. There are no poles here. This is a complex function. Cauchy's integrals tell you that if you close this loop, this integral above and below would be equal, right? If there are no poles in the middle. So analyticity is related to that, justifies that independence of epsilon here. Good. But now what has happened is that, so we have two poles. One of them has to do with the particle and the other one will be the antiparticle in the relativistic case. Here, there's only one pole. Quantum mechanics doesn't require antiparticles. There's only one pole. So there are no antiparticles. There's another lesson, which is unshelled particles correspond to the poles of the propagator. If somebody comes to me and says, I have a really, really complicated theory, here is the 2-point function of it. You take the 2-point function, you Fourier transform it in space-time. You get a function. It's a complex function. If you find a pole, that means that that theory had a particle. If you find a pole on the real axis here, that had a particle with that mass. Every pole in the propagator, remember this is super important. Every pole of a propagator corresponds to an actual unshelled particle. Now, for those of you guys who have ever looked at or will at some point look at, I don't know if we're going to get to this in this semester, but unshelled particle means stable. The particle can propagate forever. if the particle is not stable, it's unstable, it won't be a pole, it would be a bump in momentum. When you Fourier transform, you see a bump. That has a name in physics. We're going to come to that hopefully in the semester. What's it called? Resonance. That's what a resonance is. It's a short-lived particle. All the particles that have mass, like gauge bosons that have masses and are not stable, they will show up as the resonances in the two-point function. We usually do not measure two-point function. You're gonna see that in LSZ. So here's the thing. Now anticipation what's gonna happen. There's something called LSZ that relates the two-point function or correlation function to the S matrix. The poles here or the bumps here will correspond to the bumps and poles in the cross section. So we're going to comment to that. But if you are a particle physicist, that already resonates. All right. Any questions? We'll come back to resonances. I think we must come back because I'm teaching LSC. All right. So how am I doing on time? Ooh, I gotta speed up. Oh, I said this. So in relativistic free scalar field, propagator had poles as zeros of this, right? And these are on shell. Virtual particle, you might have heard of the word virtual particle. That means an off-shell configuration, right? It means an off-shell configuration. When you do path integrals, the on-shell configuration is the configuration that's like classical equations of motion. The off-shell ones are the ones that are not, and they're suppressed. All right. A little bit more about, yeah.
Can you explain again what the shell is?
What is a shell? I don't know what is the right way of describing it. I don't know why people call it, but remember the representation theory boson, right? What did we draw? It was omega k was fixed in terms of k, right? How was it? If this is energy, if this is k naught, right? So k naught squared minus k naught squared plus k squared is m squared, or minus m squared, that's the normalization. So it corresponds to this thing, right? On shell is when you are sitting on this Dirac delta function, right? This Dirac delta function k mu minus m squared, when things are like this, or plus m squared. Right? Off shell is a field configuration that's not here, somewhere else. They appear in the path interval. Right?
So for in or out of the shell, is that relevant?
You're either on shell, which means stable particle, or not.
We can also argue for that, like when you draw the Feynman diagram, so whatever that appears out of the loop, those are the on-shell things. So he said
Only on shell stuff could be asymptotic states. Yeah. All right. So a little bit of just a reminder about green functions. Do I need to do this, or do you guys? Let me do it quickly. Okay. So what is a green function? Green function, before talking about green functions, let me just tell you about a simple setup. You have a matrix K. Forget about green functions for now. You have a matrix K, and there is another matrix that's multiplying it on the left, and it gives you identity. What is this matrix? That just means that it's the inverse of K, or K is the inverse of that. All right, everybody's with me? Good. So now imagine these were continuous variables. This Kronecker delta becomes a Dirac delta. Matrix, these guys will have two continuous variables, z and y. This is matrix multiplication. Okay. Now what you have is some differential operator, for example, this, acting on K will give you this. Let me just, let's just focus on this for now. So this is just a continuous version of this equation. And you will find this, there's a sense by the extension of the same logic, you could think of L as inverse of K, left inverse of K. All right. Now, often in physics, we're interested in these L's that are, remember this as a matrix? It's like, think of it as they're almost diagonal. So if I have a matrix like this that you just saw, what does this look like in the continuous limit? Second derivative. Does that make sense? This looks like second derivative. If you have higher derivatives, the matrix will be occupying multiple rows around the diagonal. But in the continuous limit, these are like discretization of differential operators, right? So a particular type of differential operator is Lx delta xy. That just means diagonal. Good. And then K, you could take it to be only, you could take this to be only a function of x minus y and x minus y for translation invariance. You end up with the following setup. So let's Fourier transform kx minus y and Lx minus y. This relation after Fourier transform gives you this. Lk is kk equal 1. This is just a Fourier transform of this expression and just a Fourier transform of this. All right. So indeed, once you Fourier transform, now this is pretty clear that L is like 1 over k. What are we solving? We had this equation. Our L of x and z was the Schrodinger operator. Our propagator was the green function for the Schrodinger operator. You Fourier transform the Schrodinger operator, right? It becomes this. Acting on the Fourier transform of propagator is equal to 1. So the propagator is 1 over this. Right? I don't need to do any of those integrals. That's why green functions are nice. How does the story change in the relativistic case? You have the Klein-Gordon operator. You're looking, your propagator is the green function for Klein-Gordon operator. The Fourier transform of Klein-Gordon operator is precisely this unshelled condition we've been talking about. Right? So unshelled condition, k squared minus m squared, or whatever the hell it is, acting on green function is 1. So the green function is 1 over that thing. You have to shift it by I epsilon because of invertibility. This is a very, very standard trick. Where is it? I epsilon thing. Here. It's a very standard trick in mathematics to tame violent oscillations. All right. Any questions? I have about 10 minutes left, and I think I can get through basics of the perturbation theory. All right, any questions? This is a good moment to pause. So what did we compute? We computed K naught, right? Propagator for a free particle. And we wrote all sorts of expressions, but the important one is once we Fourier transform in space and in time, we found the Dirac delta function in momenta, that was conservation of momentum. We found the Dirac delta function in time, sorry, in frequency, that was conservation of energy. What's the remainder? 1 over unshelled condition plus I epsilon. When I say unshelled condition, means the Fourier transform of the equation of motion. Right? That's what the propagator is. And it's just inversion. Green's function is just inverting an operator. All right. Next, we're going to do perturbation theory. So for a second, let's just talk a little bit physics. Imagine you're scattering two particles, meaning that two particles come in, some crap happens, and then they fly out. The potential between them is V of Q1 minus Q2. We need to solve the time-dependent Schrodinger equation, which is this. Good? This is too difficult. This is very, very difficult. We use an approximation. One particle, the approximation is that one particle is very heavy, so it barely moves. So we bring it down to a single particle, scattering off of a potential, right? So there's a fixed potential. One of them is very, very heavy, barely moves. A particle comes in, scatters off, and goes out, right? That's like, if you wish, cartoon-wise, if you think of it as a very heavy particle sitting in the middle, this guy comes in and then scatters off and goes back, and this barely feels it. So basically, think of this is replaced by potential, it just scatters off of potential. Good. All right. So what do we need to compute? This is our path integral. Let's look at this term, right? This is our propagator. The propagator is still same expression. It's still the amplitude for Qi, Ti, Qf, Tf, right? This is what we want to compute. So there is this extra factor of e to minus IH bar integral Ti, Tf, dTv. It's the contribution of the interactions to the action. What we would like to do is to expand this expression as 1 minus IH bar integral Ti, Tf, dTv q blah, blah, blah. Why am I allowed to do this expansion? Sorry. You could only expand a dimensionless parameter. So action in units of H bar are small. So I'm allowed to expand it. But if you think about this, this is kind of crazy. It's not, we're not saying that the coupling is small. Right? This is what I'm trying to say. We are saying that the contribution of the coupling to the action divided by H bar is small. So another way of saying is that coupling is small, but compared to what? When you're talking about, there's an integral over space, right? So it is a tricky approximation. I want you to keep that in mind. But let's just push forward. All right, so what we're gonna do is that this term is K naught, our old K naught. The next order term, we're gonna call it K1. And it's gonna be just the same thing with this guy down here as an operator inserted. So we're gonna calculate K naught. In anticipation for me running out of time, let me tell you that this expression K naught, we're gonna write it as the following. It's gonna look like, so K1 is gonna look like something that we're gonna draw this way. It's just, these are some, what these are short form notation for you to read the integrals, but we'll see. So the K1 will look like this, K2 will look like K naught, V, K naught, V, K naught. This is the fourth order. So we're going to come up with some sort of diagrammatic way of representing our integrals. When I draw this picture, this means an awful integral, right? All right, so let's do that. Let's do that only for K1 because we're out of time. All right, first order approximation. Remember that my sigma was this, right? So my K1 is, let me just write it again, is integral of, you see, sometimes I mix both notations, which is funny. dqt e to the power of I s naught over H bar minus I over H bar integral of Ti Tf dt vq t. Right? That's what I'm trying to compute. So as before, to compute this, so this minus 1 over H bar is this. I know that this bit will have this divergent piece that's coming from the momentum path integral, right? And notice that my potential doesn't have momentum dependence, so I can still do those steps, right? Then this integral over t, I'm discretizing as d of t, right? This is the expression that I had previously for the propagator, just I of S naught over H. This is my V of Qj Tj, and then I'm going to insert resolution of identity in the middle, as I did before. So this is the expression we're trying to compute. Okay, you can read this. Let me draw this on the board because I'm really running out of time. Let me draw this on the board with pictures, but you can see that, read the intervals and see how it's done. I'm just going to describe it to you. What's beautiful about these Feynman diagrams is that they're beautiful. What I'm supposed to calculate is the following piece. Oh, sorry. Oh, that's good, actually. That's good. I'm a little bit concerned about presentation. All right, well, you'll read the intervals, but you'll see. So, what is this? I'm doing a path integral. This is Ti, Tf, over all path. There is some Qi here, some time Ti, and then there is some Qf here. Good. I pick a path. Well, what I'm gonna do is I'm gonna associate to this path this action, but at some point there is an operating exertion, V of Q prime at some time T prime. So how am I going to do this integral? At here, I'm going to insert a resolution of identity Q prime T prime, Q prime T prime, right? That means that when I insert this resolution of identity, this V of Q comes out. What I obtain is V of Q prime, a propagator from here to Q prime, propagator from Q prime to Q prime. Right? So let me write it. There's just one, I isolated one single term. So this is going to look like this. It would be propagator K naught of Q of F T prime, Q prime T prime, Q of Q prime T prime, QI TI. So let's write this as Q naught V Q naught, K naught V K naught, and I'm gonna draw it symbolically this way. Now, if you follow the perturbation theory, I have to integrate. The first order correction to the propagator is integrate over this, over anywhere in Q and anywhere in time. So in this expression, this V is integrated over anywhere in space and time. Just do the perturbation theory for yourself, you'll see. Right? This is the structure of the first order approximation. The integrals are in the notes, but you'll see what it is. Any questions about this? As you go to the next order, it will, perturbation will take the following form. So now you have to insert two V's anywhere in space, time, right? So they will be propagated to the first one, propagated to the second one, propagated to that one. You might worry about time ordering. You don't need to. These are Feynman path integrals. Everything is time ordered. Right? So there is this that comes out. Structurally, the structure of perturbation theory looks like this. I shouldn't call this Feynman path integral. These are called Born series. The Kn term is minus I over h bar 2 power of n, integral of dt1 to dtn, dq1 to dqn, this structure. Then we diagrammatically write it this way. Right? What is this approximation? This is very physically intuitive. Can you see? Can you interpret it? It's
It's like a street.
you could say that. You could say that. But let me give you this physical picture. The propagator, the particle is propagating from this point to this point. In some background potential. The background potential will interact with it at some time, q prime, t prime. So you could view it this way. It's as if it's a free particle. The particle is moving for free at some point and some moment, there's some sort of interaction in space-time that happens, and then the interaction is done, it propagates freely. But now that interaction can happen anywhere in space and anywhere in time, so integrated order. The next order term is when the interaction is strong, it happens twice. It's like view it as like, that's basically the cartoon picture. This is the cartoon. This is not literally true. Right? Of course, it's not literal. These are Feynman path integrals. But this is the picture to have in mind. In perturbation theory, that's what you're doing. You assume that nothing happens for a while. Part of the path integral. Then something happens. Then nothing happens. Something happens. And the number of times that something happens, if it happens n times, that's the nth order of perturbation. All right. Any questions? I managed. Oh no. Any questions?
Why did it not like gain a phase?
Gain a phase.
It's like action is assigning a phase to each of the paths. Or like
So action is local. So I can do that means that I can do my integral from here to here, and then a brand new integral from here to here with some new boundary conditions. And that's what I'm going to do. In the middle, I'm going to insert an operator. And because this is the basis I'm expanding in, that operator is just a function in space. Right? That's all we're doing. Hopefully you see how important locality is in all of this. Yeah.
So path integral is manifestly local, right? You can never do
Must be, yeah. Well, no, I take my words back. We're dealing with local path integrals. I just wrote a paper about non-local effects of path integrals, so I'm not going to say that. But yeah. In perturbation theory, it will be because we're brainwashed by perturbation theory in this course, we're always talking about local actions and local expression, and it's essential for us to stick to locality. The rule is this: if you can make it local, you must make it local. Even if it comes at the cost of inventing unphysical stuff. Sometimes you cannot make it local. Then you deal with it. All right. Thank you so much, guys. Yeah.
Is this the same physical idea behind Gelman and Lowe?
Gelman and Lowe, what?
You have the correlation function for the interacting vacuum in terms of the free vacuum.